Hey, welcome back. If you've spent any time in reinforcement learning, you've probably heard the term policy gradient thrown around in papers in libraries like Stable Baselines or CleanRL, or as the foundation behind algorithms like PPO, A3C, and SAC. But what actually is a policy gradient? Where does it come from? And why does training with it feel like trying to teach someone to ride a bike by only telling them that was good? Or that was bad? No details, no corrections, just vibes. That's exactly what we're going to unpack today. This video covers three core topics: reinforce, the original policy gradient algorithm and the mathematical trick that makes it work; variance reduction, because naive policy gradients are brutally noisy, and we'll see why and how to fix that; stochastic versus deterministic policies, two fundamentally different philosophies for how an agent chooses its actions. By the end, you'll not only understand the math, you'll have the intuition to debug why your policy gradient runs aren't converging, and you'll see how these ideas connect to modern algorithms you're likely already using. Let's get into it. Before we derive anything, let's ground ourselves in what we're actually trying to optimize. In reinforcement learning, the goal is to find a policy, let's call it pi subscript theta, parameterized by theta, that maximizes the expected cumulative reward, which we write as j of theta equals e sub tau over pi sub theta of r of tau, where tau is a trajectory, a sequence of states, actions, and rewards, and r of tau is the total return of that trajectory, usually the discounted sum of rewards. Now here's the core challenge. How do we compute the gradient of j theta with respect to theta? If we knew the full dynamics of the environment, every transition probability, we could compute this analytically, but in most interesting problems, we don't. The environment is a black box. We just sample from it. So we need a way to estimate del theta j of theta from experience alone. That's the entire game. There are three broad approaches to solving this in RL: value-based methods, like DQN, learn the value function, and derive a policy implicitly via greedy selection. They work great for discrete actions, but break down in continuous or high-dimensional action spaces. Policy-based methods directly parameterize and optimize the policy. They can naturally handle continuous actions and stochastic policies, but are typically less sample efficient. Actor-critic methods combine both, and that's where modern algorithms like PPO and SAC live. But to get there, you first need to deeply understand pure policy gradients. All right, here's where the magic happens. We want to compute del theta j of theta equals del theta e sub tau over p sub theta of r of tau. Let's expand the expectation by writing it as an integral over all possible trajectories, equals del theta integral p theta of tau r of tau d tau. Now, and this is the key step, we want to bring the gradient inside the integral. The reward r of tau doesn't depend on theta at all. Only the trajectory probability p sub theta of tau does. So, equals integral del sub theta p sub theta of tau dot r of tau d tau. Here's the problem. This is still an integral over all trajectories, which we can't compute directly, but we can turn it into an expectation again. And that's where the log derivative trick comes in. Here's the trick, and it's just calculus. Del theta log p theta of tau equals del theta p theta of tau over p theta of tau. So, del theta p theta of tau equals p theta of tau times del theta log p theta of tau. Substituting back, del theta j of theta equals integral p theta of tau times del theta log p theta of tau times r of tau d tau, which is now an expectation, equals e sub tau tilde pi sub theta del sub theta log p sub theta of tau dot r of tau. This is Monte Carlo estimable. We just sample trajectories, compute the reward, compute the log probability gradient, multiply them, and average. That's reinforce, but wait, what does del theta log p theta of tau actually look like when we expand it? A trajectory has probability p sub theta of tau equals p of s sub 0 times product over t of pi sub theta of a sub t given es sub t times p of s sub t plus 1 given es sub t comma a sub t. When we take the log p sub theta of tau equals log p of es sub 0 plus sum over t of log pi sub theta of a sub t given es sub t plus log p of es sub t plus 1 given es sub t comma a sub t. Taking the gradient with respect to theta, the initial state distribution and transition dynamics have nothing to do with theta, so they vanish. Del theta log p theta of tau equals sum over t del theta log p theta of at given st. Beautiful. The environment dynamics disappear. All we need are the log probabilities of the actions we took under our own policy. So the final reinforced gradient estimator is del theta j of theta is approximately 1 over n times the sum over I of the sum over t of del theta log pi of at to the power of I given st to the power of I times r of tau to the power of I. In code, this is deceptively simple. You run your policy, collect a trajectory, compute the total return, and update. Python loss equals minus torch dot, sum open parenthesis log underscore probs, times returns, close parenthesis, loss dot backward, open parenthesis, close parenthesis, optimizer dot step, open parenthesis, close parenthesis. The negative sign is because we're doing gradient ascent on J, but optimizers do gradient descent on a loss. That's reinforce. Simple, elegant, and, as we'll see, with a serious variance problem. Okay, so we have a working algorithm. Let's talk about why it's often terrible in practice. The core issue is variance. Our gradient estimator is G equals the sum over T of the del theta log P theta of AT given ST times R of TO. We're weighting the gradient of every log probability by the entire trajectory's return. But think about what that means. At time step t equals 0, we're multiplying the gradient by rewards that won't happen until step 50 or 100. That introduces enormous noise. Early actions get blamed, or credited, for outcomes they may not have caused. The learning signal is so noisy that gradient updates point in wildly different directions from one batch to the next. Training is slow, unstable, and sensitive to hyperparameters. Let's look at 3 increasingly powerful remedies. Instead of using the full trajectory return r of tau, use only the future rewards from time step t onward. Del theta j of theta is approximately equal to the sum over t of del theta log pi of theta of at given st times the sum over t prime greater than or equal to t of gamma to the power of t prime minus tr of t prime. This is called the reward to go or causality trick. It's valid because past rewards can't be influenced by future actions, so including them in the gradient signal only adds noise without any signal. This is a strictly better estimator with lower variance and the same expected value. Here's another idea. What if we subtract a baseline b of s sub t from the return? Del sub theta j of theta is approximately equal to the sum over t of del sub theta log pi, sub theta of a sub t given s sub t times open parenthesis r sub t minus b of s sub t close parenthesis. This is still an unbiased estimator, as long as b doesn't depend on the action, because e sub theta of del sub theta log pi sub theta of a given s times b of s equals 0. This can be shown by noting that e sub a of del sub theta log p sub theta of a given s equals 0 for any policy. The most common and effective baseline is the value function v of s sub t. an estimate of how much total reward you'd expect from state S sub t onward. When you subtract v of s sub t, the quantity r sub t minus v of s sub t has an intuitive name, the advantage a sub t. A sub t equals r sub t minus v of s sub t. Positive advantage. This trajectory did better than expected. Push up the probabilities of those actions. Negative advantage. This trajectory underperformed. Push them down. This is a much more informative and stable signal, and this is exactly where you arrive at actor-critic methods. The actor is the policy pi theta, the critic is the value function v phi. They train jointly, with the critic providing low variance advantage estimates to the actor. The state-of-the-art variance reduction technique in modern RL, used in PPO, is GAE, introduced by Schulman et al. In 2016. The insight is that there's a bias-variance trade-off in how far you look ahead when estimating the advantage. GAE blends estimates at every horizon with an exponential decay controlled by a parameter lambda. A sub t to the power of GAE of gamma comma lambda equals the sum from L equals 0 to infinity of gamma lambda to the power of L delta sub t plus L, where delta sub t equals R sub t plus gamma v of S sub t plus 1 minus v of S sub t is the TD residual, a one-step advantage estimate. Lambda equals 0, pure one-step TD, low variance, high bias. Lambda equals 1, Monte Carlo return, low bias, high variance. Lambda in the interval 0 to 1, the sweet spot. PPO typically uses lambda equals 0.95. Understanding GAE is critical to understanding why PPO trains as stably as it does. The policy gradient itself is the same. What's changed is the quality of the advantage estimate. Stochastic versus deterministic policies. So far, all of our policies have been stochastic. P theta of a given S gives a probability distribution over actions. But there's a whole other family of policy gradient algorithms built on deterministic policies, where the policy directly outputs a single action. A equals mu theta of S. Let's understand the difference deeply, because it's more than a technical detail. It's a design choice with real trade-offs. Stochastic policies. A stochastic policy outputs a probability distribution. For discrete actions, that's a categorical distribution, a softmax. For continuous actions, it's typically a Gaussian, parameterized by a mean and variance. A tilde n, open parenthesis, mu sub theta of S comma sigma, sub theta of S squared close parenthesis, y stochastic. Exploration is built in. The policy naturally tries different actions without any external noise mechanism. Handles partial observability. When the same observation can correspond to multiple underlying states, a stochastic policy can model the ambiguity. Convergence guarantees. The policy gradient theorem applies cleanly. At convergence, stochastic policies can represent optimal mix strategies. Where stochastic policies shine, games with imperfect information like poker, multi-agent settings, environments with aliased observations, where two different states look the same to the agent. The training signal flows through the log probabilities as we derived. The policy samples actions, and the gradient update increases the probability of good actions and decreases the probability of bad ones. Deterministic policies. Now flip the paradigm. Instead of sampling, the policy outputs the action directly. A equals mu theta of A as. The gradient of the objective with respect to theta can now be computed directly through the Q function using the deterministic policy gradient, DPG theorem. Del theta j of theta equals E sub S of del theta mu sub theta of S dot del AQ to the power of mu of S comma. A given A equals mu sub theta of S. This is the Silver et al. 2014 result that spawned DDPG, deep deterministic policy gradient, and later TD3 and SAC. Why deterministic? Sample efficiency. The gradient doesn't require averaging over action samples. You can propagate it directly through the Q network into the policy. Low-dimensional exploration. Exploration is handled separately, typically by adding Gaussian noise to the action. A equals mu theta of S plus epsilon. Epsilon is approximately normal with mean 0 and variance sigma squared. Better for high-dimensional continuous actions. When your action space is 17-dimensional, like a humanoid robot, sampling from a distribution is expensive and noisy. A deterministic policy is much cleaner. Where deterministic policies shine: robotics, continuous control, Mujoko, Isaac Jim, locomotion tasks, any setting where precise, repeatable actions matter. The SAC bridge. A nuanced middle ground is soft actor critic, SAC, technically a stochastic policy, but one that uses the reparameterization trick to get deterministic style gradient flow. A equals mu sub theta of S plus sigma, sub theta of S times epsilon. Epsilon is approximately normal with mean 0 and identity matrix. By factoring the randomness into a noise variable epsilon that's independent of theta, you can backpropagate gradients directly through the sampled action. You get the exploration benefits of a stochastic policy with the gradient efficiency of a deterministic one. SAC also adds an entropy bonus to the reward, encouraging the policy to remain stochastic and explore widely. J of theta equals E of the sum over T of R sub T plus alpha times H of pi of S sub T. This makes SAC one of the most stable and sample-efficient off-policy algorithms available today. Summary. All right, let's bring this home. We started with a deceptively simple question. How do you optimize a policy when the environment is a black box? The answer is the policy gradient, and specifically, the log derivative trick that lets us turn an intractable integral into a Monte Carlo estimator we can compute from experience. We saw how reinforce, while mathematically elegant, suffers from high variance. And we looked at 3 progressively powerful solutions: reward to go, baselines and advantages, and generalized advantage estimation. And finally, we compared stochastic and deterministic policies, 2 different philosophies that lead to 2 different families of algorithms, each with distinct strengths depending on your problem. Here's the key insight to carry with you. Policy gradient methods are not one algorithm, they're a framework. Reinforce is the foundation. Every modern algorithm, PPO, A3C, DDPG, TD3, SAC, is essentially a policy gradient method with carefully engineered variance reduction, stability tricks, and sampling strategies layered on top. If you want to go deeper, the next videos in this series cover PPO in depth, the clipping objective, why it works, and implementation gotchas. SAC from scratch, building the full soft actor critic algorithm step by step, debugging RL training runs, because knowing the theory is only half the battle. If this was useful, subscribe and drop a comment with what you'd like covered next. See you in the next one.